Okay, Luca, let me introduce shortly your presentation. So today we have extraordinary event, very nice presentation of Professor Luca Pattavina from Universita di Milano-Bicocca. And Luca will told us about, from my point of view, super interesting project, Res Nova, which is a revolutionary archaeological led observatory for astrophysical neutrino sources. I like it very much because it's, from my point of view, it's possibility to go with neutrino astronomy with 100 kilogram, not kiloton detectors. So, Luca, welcome to our winter seminars and to Institute for Nuclear Research. People also join this meeting.
Okay, so thank you very much, Fedor, for the introduction, and also thanks to Vladislav and Vladimir for the kind invitation. I'm very happy to be here. Unfortunately, online, but it's better than nothing. So, yes, as Fedor said, today I will be talking about the Res Nova project, a project that was recently funded by the European community, and this project is aiming at detecting neutrinos produced from astrophysical sources and mainly supernovae, while using an array of cryogenic detectors made of archaeological lead. So we know very well that there are many nice running experiments that want to observe and detect neutrinos from supernova. Well, with this project, we would like to see if we can open a new path, a new way for detecting these neutrinos in a different way and possibly more interesting way. So we know very well that experiment like Borgsino, LVD, they made the history of astrophysical neutrino detection, but I think this could be a good time for changing and open, as I said before, anyway. So when we talk about supernova, we know very well that we need to wait a long time for observing a supernova. And so this, many people could think that this is a boring activity. However, in my opinion, I think there are other activities which are way less interesting than waiting for a supernova. And here I found an example online. And this is one of the longest running experiment. It's an experiment that started in 1927 in Australia, where Professor Mason wanted to demonstrate that pitch asphalt is a highly viscous fluid and is not a solid. And for demonstrating this, he poured some asphalt inside a funnel here, and he was just waiting for a drop to come down the funnel. And over 100 years, he and his collaborator, they observed almost, let's say, nine drops. So still something which is faster than a supernova rate in our galaxies, but way less interesting than observing a supernova. So I would say this could be a good reason for focus our attention on supernova detection, in particular neutrino detection from supernovae. So about the Res Nova project, this is one single slide that I try always to show for providing a summary, let's say, overall picture of the experiment. We know that supernovae are among the most energetic and interesting events in the universe, where a very large number of neutrinos of all different flavors are produced. But unfortunately, our understanding of this unique phenomena is limited by the fact that, and on one side, the supernova are rather rare, and depending on the model, this rate in our galaxy can go from one supernova every 30 to 60 years. So 50, I would say, is a rough average. And on the other side, this study is difficult due to the fact that even if you are running very large volume detectors, we are only sensitive to a fraction of the neutrino emission. So from our point of view, it would be beneficial if we will be able to detect from the next galactic supernova as many neutrinos as possible, obviously, and of all different flavors. And if we could ask for more, or why not? If it would be nice if we could do this with a small size detector, something that could easily be made, let's say, in a conventional lab. And this is actually possible. And the best channel to do this is the coherent neutrino nuclear scattering process on lead nuclei. And with this process and this target material, we can achieve a cross-section on neutrino interaction, which are more than 1,000 times higher than the conventional use channel. And so from this point of view, you can really see that we can get we have a really unique opportunities to detect supernova. And so for RESNOVA, we want to build a technology demonstrator, a neutrino telescope that despite the small size and the total volume of this detector will be equivalent to a cube of 30 centimeter size, so something really compact. And with this detector, we could survey almost the entire Milky Way galaxy for supernova events. And this detector will be made with lead, not any kind of lead, but with archaeological lead. And so the core of the project is this, to use archaeological lead, a material which is not meant for science application, let's say, and use it to run one of the most advanced, let's say, neutrino detector. So in just a couple of slides, I would like to give a short introduction about the supernova. What is a supernova, and what is interesting about supernovae? So what is a supernova? This is a highly energetic explosion that marks the end of a star's life. And during this event, almost the entire beaming energy of the star is released as neutrinos of all different flavors, as we said, but also gravitational waves and electromagnetic radiation are released. Here in this photo on the left here, we can see a supernova in the light channel. And this is as bright as a full galaxy. So this somehow gives us an idea that even if light is a tiny amount of, say, electromagnetic radiation, it's only a tiny fraction of the emission, this is as bright as a full galaxy. And so this tells us that the amounts of neutrino which are produced is enormous. And why do we want to focus on neutrinos? Well, there are different reasons. And here I've selected only 3 of them, which I believe are the more interesting. So to help understanding why neutrinos are interesting, let's have a look at this plot. Here we see a neutrino-driven core collapse simulation. On the y-axis, we can see the luminosity of the different components of the emission, neutrinos, gravitational waves, and electromagnetic radiation, as a function of time. And obviously, we see that neutrino are the most intense components, the emission with the highest luminosity. So this is the ideal channel to be used for studying supernovae. Then the second aspect is that the neutrinos, which are produced inside the stellar core, and the core is almost transparent to neutrinos, then we can really use these particles for studying the astrophysical reaction and the dynamics that are driving the supernova explosions. And so we can really use these particles as probes and messengers for studying supernovae. And especially because there are specific features in the time emission, in the time distribution of this signal. And then the third aspect, which I think is also extremely interesting from, say, a perspective point of view, is the fact that neutrinos are actually produced even before a supernova explodes. So we can really use these particles to send alerts to the scientific community, such that we can perform, in principle, a multi-messenger observation of such astrophysical event, and so perform a simultaneous detection of gravitational waves, neutrinos, and electromagnetic radiation. And this is something that can be considered as one of the holy grail of astroparticle and astrophysics. We said the neutrinos would be nice to detect them, and this actually was already done many years ago. And for the first and only time, there were neutrinos produced from supernova 1987A. And this was very far away, was in the Large Magellanic Cloud, 50 kiloparsec away. And say most of the knowledge that we currently have about supernova relies on the few neutrinos, about say 25-ish neutrinos that we were able to detect with many different experiments that were running at that time. But so you may say, okay, we already learned enough about supernova. Well, the answer is no, because the observation, the detection of neutrino that we made was not ideal at all. Actually, there were many small problems that now we are able to solve, and that could make the next observation really unique. And there are 4 different aspects that could be improved, and we will have a look at them now here in this slide. And the first one is that the neutrino that were running, neutrino detector that were running in the 80s, the most sensitive one were the Kamiokande experiment in Japan, the IMB in US, and the Baksan detector in the Baksan laboratory. And all this experiment observed an excess of neutrino events above their background, and unfortunately, these detectors were not synchronized among them. There were not GPS available at that time for scientific purposes. And so the fact of being able to combine, overlap all these neutrino emission was not possible. And so something very rough that we do now is only align the first neutrino event and then provide a single picture of the neutrino emission. And so from this point of view, there is something that can be improved now, and this is already very well done by many experiments thanks to the technology available. Then the second aspect is, which is, I think it's very interesting, it concerns the Mont Blanc experiment, the LSD experiment. And this experiment observed a big excess of neutrinos some minutes before the observation of the Kamiokande IMB and Baksan experiment. And so there is no clear explanation for this. Some people said, yes, this could be the burst of neutrino before the explosion, some sort of pre-supernova neutrinos. But we still don't have a clear understanding of this emission and how the observation of the Mont Blanc is comparable or connected with the other observation. And so from this point of view, now we have a nice and good network of detectors all over the world, which are very well synchronized and are able to also provide a cross alert, cross trigger in case of a supernova emission. The third aspect is shown here and concerns the neutrino flavor detection. The experiment these experiments were mostly sensitive to electron antineutrinos, and so we were only able to observe, one single neutrino flavor, and so we were only able to get a limited picture. Given that with the current knowledge that we have, we know that all different neutrino flavors are produced in supernova. Being able to observe all these different families would be ideal. And this is actually what, with the RESNOVA, we are aiming at. And then the first interesting aspect, something that hopefully will come the next year, but already in the 87, we were really that close, is the observation of gravitational waves and neutrinos simultaneously. And in Rome, the GeoGrav experiment was an experiment of the Professor Amaldi, and people from the Amaldi group observed an excess of energy released in their gravitational wave antenna. And this was, they look at the time of this excess of energy, and this was compatible with the observation of the Mont Blanc experiment. So it was like, wow, we already got in the 87 simultaneous detection of gravitational waves and neutrinos. But actually, given the not clear understanding of the Mont Blanc observation, and then given that the excess of energy observed in this antenna was too large to be compatible with a signal coming from the Large Magellanic Cloud, then this was rejected as a possible simultaneous observation. But this overall picture tells us that this field is very active since 1987, and after almost 40 years, we are still, looking for the same things, trying to get the same understanding, but now the technology that we have in our hands could make things way more interesting and also easier for having a full comprehensive understanding on the supernova physics. So how does a supernova explode, and how neutrino can play an important role in this aspect? Well, this is shown in this slide. In this slide here, in this plot on the left, we can see an hydrodynamical simulation of the neutrino transport inside a supernova. And in this plot, we can see here on the y-axis still the neutrino luminosity, and you can have a look at the scale. The amount of energy which goes into neutrino is a huge amount, 10 to the 56 MeV per second of energy goes into neutrinos. And the x-axis, time scales of the order of few seconds, so a very short burst with a specific structure in the neutrino emission, as is shown here. And we can see the different colors, different neutrino flavors, and neutrino X here stands for muon or tau neutrinos. And so there are different structure in the neutrino emission, and all these structure are connected with the interaction and production of neutrino inside the stellar core. So we can identify about, say, 4 main phases in the neutrino emission. And the first one is a pre-supernova emission, which is something that comes before the supernova explosion. And this can be compared with a conventional solar neutrino emission. So standard fusion reaction that produces neutrinos. Then once once light elements are burned and produce heavier and heavier elements, we start to produce silicon and finally iron. Iron is produced inside the stellar core. At this point, it's not anymore energy favorable to burn iron to produce energy, and we will start to have a collapse of the star if this star has a large enough mass and reaches the Chandrasekhar mass. At this point, the gravitational force of the iron core will start to pull down the outer envelope of the star, and this matter will start to form supersonically. And we will start to have a neutronization of the core, which means that free protons will be dissociated from the iron nuclei, will capture electron and will produce neutrinos. At this point, we have a stiff neutron core. This infalling matter will bounce off this stiff nucleus, and a shock wave, an outgoing shock wave, will be created. And this shock wave, which is going outwards, will meet the matter that will start to fall, and we will start to have an accretion of this shock wave. And this is the time where neutrino play a crucial role, and this neutrino will transfer a lot of energy from the stellar core to this shock wave that will lead finally to the final explosion and stellar cooling. And the stellar cooling, which is the longest phases, which lasts about 10 seconds, and is the time where most of the neutrinos are actually released. By studying the neutrino emission in all these different phases, so neutronization, accretion, and cooling, we can really test our understanding, our knowledge of physics in many different sectors, and use supernovae as astrophysical laboratories, because we can perform study on stellar neutrinos, so studying the properties of stars. We can, by looking at the neutronization phase, we can perform neutrino physics studies and perform neutrino mass measurement and understanding the possible neutrino mass hierarchy by exploring this burst of almost pure electron neutrinos. By studying the accretion phase, we can get information, detailed information about the corpuscular physics and about the properties of the supernova remnants, whether this is a neutron star or a black hole. And for example, by studying the neutrino emission in the cooling phase, where we'll have a large number of neutrinos, we can perform physics studies for physics beyond the standard model in the neutrino sector, and also provide information about nuclear astrophysics, because this is the time where also heavy elements are produced, and neutrino can play a crucial role in this it's a stellar outburst where the stellar envelope outer layer are ejected in the space. And but let's get let's say a closer look about the neutrino properties. And in these plots here are shown the same data of the previous simulation, but here we want to look at different parameters. In the specific, on here on the left, they shown the neutrino flux at the Earth from a 10 kiloparsec explosion as a function of the neutrino energy, so neutrino energy spectra. And still same color, different neutrino flavors, and the dashed line is the total neutrino energy spectrum. And here we can see that neutrino X, so the red and green curves, are the most intense component of the emission. And then, given that these are almost a thermal, quasi-thermal distribution, we can have a look at the average neutrino energy and look at the distribution of this average neutrino energy over time. And also in this case, we can see that muon and tau neutrinos are the most energetic component. And so this is the reason why I think it's extremely important to look for a channel which is able to detect all the different neutrino flavors. And given that the current running experiments are mostly sensitive to electron antineutrinos, well, we are really missing somehow a tool, a screwdriver to unlock the observation of all the other neutrino flavors with high sensitivity. How do we detect neutrinos? Well, this is sort of a summary on the available techniques for detecting neutrinos and specifically supernova neutrinos. Since 1987 and until now, we are mostly exploiting the inverse beta decay, as you already said at the beginning of this talk. But we are also exploiting the elastic scattering on electrons, especially for two reasons. First, because it's a way of being sensitive to muon and tau neutrinos. But in this case, the cross-section is more than one order of magnitude lower than the inverse beta decay one. And on the other, this channel can be extremely interesting because the momentum kept by the electrons can provide information about the directionality of the incoming neutrino. So can provide information about the position of the supernova in the sky, and so providing pointing information. And then lately, with the development of advanced liquid scintillator, then also elastic scattering on protons start to be within the reach. And this is also one of the channels that the Juno experiment is aiming at exploiting for detecting supernova neutrinos. But in this talk, I would like to focus mostly on the coherent elastic neutrino nuclear scattering process that will be exploited by the Resnova experiment. And this is a process that was observed for the first time in 2017, so a few years ago. And it took a lot of time since the first postulation of this process. This is actually was proposed in 1975, I believe. The possible use of this channel for detecting neutrinos. And it took so many years, 40 years, to detect it for the first time because of we were lacking of suitable technology to detect low energy nuclear recoil, which are produced by the neutrino scattering. And let's have let's have a closer look at this process. This is a process where the neutrinos scatter off a nucleus, as I said, and induce a low energy nuclear recoil. And as a rule of thumb, a 10 MeV neutrino, like a supernova neutrino, can induce a nuclear recoil of the order of 1 keV. But obviously, this 1 keV will depend on the size, on the mass of the nucleus. This is a neutral current process, so it's equally sensitive to all neutrino flavors. And when the interaction is coherent, then we have a strong enhancement of the cross-section. With coherence, we mean that the neutrinos can see the nucleus as a single body and will not interact with the single nucleus, but will be a single interaction, as I said, that will induce a nuclear recoil. The cross-section of this process can be derived by standard Mosaic basic principles, and is as follows. It will depend on the square of the neutrino energy. It will depend also on the nuclear form factor that describes how much the interaction is coherent, and will depend on Q, which is the momentum transfer. And then it will also depend on the weak nuclear charge, given that this is a weak process. And for a spin zero interaction, if you do the math and consider all the couplings of neutrinos with all the different quarks of the nucleus, then for a spin zero interaction, then we can neglect the axial coupling, and what we are left with is this formula, where n is the neutron number of the target material and z the proton number. And this proton number will is connected with the Weinberg angle as a coupling. And so given that this part in parentheses gives only, it's a small number, so gives the proton contribution is extremely small, and we can perform the brutal approximation stating that the cross-section will depend only on the neutron number. And so the cross-section will scale as the square of the neutron number of the target material. And so from this point, we can understand why lead is so interesting. In fact, this is the only element of the periodic table that can show simultaneously the highest neutron number for a high cross-section and the highest nuclear stability to achieve low background levels. And when we look at the cross-section as a function of the energy of the incoming neutrino for different target materials using the coherent neutrino nuclear scattering, well, we can see that lead is an element with a high cross-section. Same process is shown also for germanium and silicon with the continuous line. And when we compare this process on lead with the inverse beta decay, as I said at the very beginning of this talk, we can achieve a very large cross-section, more than 1,000 times higher than the inverse beta decay, but with additional benefit of being able to detect all the different flavors. So this is really a unique opportunities that this channel is offering us. And when we try to make a direct comparison with the current technology and the opportunities that we might have with this channel, well, we can really see that these opportunities are striking. So with the current technology, we can detect only a fraction of the neutrino emission. We can do this with a small cross-section channel. And so for compensating for this and achieving large statistics, we need to operate very large volume detectors. And I mean, dimension of the order of tens of meters. While with this channel, we can detect the full composite neutrino emission. We can do this with a high cross-section channel, as we've seen. And this implies the fact that in principle, we can shrink down our detector volume while keeping the same sensitivity as the one of very large volume detector. And so this is the goal of ResNova. ResNova, we are aiming at, and we will try our best to provide a scientific community with an innovative experimental approach that hopefully will give unique insights into supernovae. And the ResNova technology is based on three key aspects, which are shown here in these different colors: the detection channel that we have just seen, the coherent neutrino nuclear scattering. Then the second aspect is the technology and cryogenic detectors. We want to use cryogenic detectors because this is the best way in which we can detect low energy nuclear recoil as the one produced by the neutrino interaction. And then as a third aspect, the target material, we want to use archaeological lead, and specifically lead tungsten crystal produced from archaeological lead, because with this material we can achieve the right sensitivity for our studies. And so the detection channel, we have seen it. Let's have a look at the technology. So cryogenic detector, we said we want to use lead, so we want to build cryogenic detector made from lead. And why cryogenic detectors? I know that I mean, many of you are involved in the cryogenic experiment, and you know very well which are the positive aspect of this, and in particular the wide choice of available compounds. Given that we want to use lead as target material, we must find a suitable compound that contains lead and that can be operated with cryogenic detector with suitable performance. And this technology gives us this possibility. Then the scalability. By developing one single detector, then if you are able to replicate this single detector many times, then you can build up a very large detector, as demonstrated by the Quarry experiment, which is running 1,000 detectors, cryogenic detectors, in this case of telluride dioxide. And then the third aspect, which I believe is the most important one, is that this technology allows us to achieve excellent energy resolution also at the energy threshold. And given that we want to reconstruct the neutrino energy, it's extremely important to have a good energy resolution over a broad energy range. And this is the case of cryogenic detectors. Obviously, there are also downsides about this technology, and I've selected just two of them here. The fact that those are fully active detectors, so they are sensitive throughout their entire volume. So suppressing the background is extremely difficult because, say, they see everything. So everything, all materials which are placed close to the detector need to be properly selected for their purity and for not providing any additional background to the experiment. The second downside is the fact that those are slow detector. So we need to reduce in all possible means the detector counting rate, and the first thing to be done with cryogenic detector is to run them underground. This is the best way in which we can reduce the detector counting rate and in principle reduce to a zero level possible muon induced backgrounds. The working principle of cryogenic detector, I know, I think that all of you know it very well. I just want to say 2 words about this and give some numbers to give an idea about the difficult aspect of this technology, because I mean this technology is extremely nice, but also not simple to be run. And the working principle is simple. This is a highly sensitive calorimeter, which is operated at cryogenic temperature, or there are a few millikelvin. The low temperatures is needed in order to reduce as much as possible the heat capacity of the absorber. And for conventional crystal absorber used as cryogenic detectors, at 10 millikelvin, the heat capacity is of the order of few picojoule per Kelvin. And this means that for an energy deposit of 1 keV, we will have a temperature variation of 1 microkelvin. So this tells us that we really need to develop highly sensitive thermometers that are able to first observe such a small temperature variation, and second, that are extremely stable over time, because we want to detect, as said, small temperature variation. But this technology, obviously, we are not the first one to exploit this technology. This is something that has been developed in the last, let me say, 30, 40 years, and we can take full advantage of this. And we were able to obviously run many detectors, and we have selected lead tungstate as our crystal candidate for many different reasons. And in this energy spectrum here is shown the operation of a lead tungstate crystal produced from commercial lead. We can highlight the 2 aspects from this plot, and the first one is the energy resolution of this detector. You can see that we can see these sharp lines over a broad energy range from few keV up to MeV, so showing that really we can achieve excellent energy resolution. And then the second aspect is that this detector had a very high counting rate. The mass of this detector was about 0.5 kilos, and it was affected by an overwhelming background of natural radioactivity embedded in the crystal, inside the crystal. And so we needed to develop a technology way in which we could reduce or mitigate these possible backgrounds. And so in this case, we took advantage of the fact that lead tungstate is also an efficient scintillator at low temperature. And so in principle, if you are able to place a light detector, in this case a cryogenic auxiliary detector next to the crystal absorber, then we could detect the light, the scintillation light simultaneously with the signal, the temperature signal induced in the main absorber, and we could perform this kind of plots, 2-dimensional plot, where the same data shown here are also shown here. In this plot, we show the light yield as a function of the energy deposited in the main absorber. And so by reading out the scintillation light, we could also perform a particle identification and possibly suppress unexpected background contribution in our region of interest. As you can see, we can identify electron gamma interaction, but also alpha interaction, and possible also neutron-induced nuclear recoil. So for SNOVA, we want to develop highly radiopure lead tungstate crystals, taking advantage of the knowledge and know-how that was achieved and obtained in the neutrinoless double beta decay sector, where ultra high radiopure crystals are developed for the investigation. And we want to combine this technology, this know-how, with the one of direct dark matter searches, because dark matter experiments are searching mainly for low energy nuclear recoil induced by dark matter particle, and this is the same type of signature that we are looking for. In this case, we want to exploit the temperature sensor technology developed for these dark matter searches, and we will use lead tungsten crystal coupled to transition edge sensors as a thermal sensor, because this technology allows us to achieve extremely low energy threshold. And so this is what concerns the technology, cryogenic detector with lead tungsten crystal. And then we come to the third point, archaeological lead. Why archaeological lead? Well, I would say that the first answer is that because it's nice, can be extremely attractive for funding agencies, but also for scientists, I believe. And then also there is somehow a scientific purpose for choosing archaeological lead and selecting this material. And in our case, we will use Roman age archaeological lead that was stored underwater for more than 2,000 years. And so from one side, cosmogenic activation was prevented by the shielding of the water of the sea. And on the other side, time allowed radioactivity to cool down. And so this material is expected to be highly radiopure. And we were able to demonstrate this by running a small sample of archaeological lead, just cut it out from a lead brick, and we have operated this as a cryogenic detector. And we have investigated the radiopurity, and this has shown an excellent radiopurity level, a level that is more than 10,000 times better than any commercially available low background lead. And so for Resnova, we want to use archaeological lead at INFN. Luckily for us, there are several tons of archaeological lead available that could be used also for our experiment. And but there is a lot of archaeological lead available all over the world, not only in INFN. And really, there is enough lead for Resnova, also Resnova 1 kiloton, as I like to say. But we will not need to build a Resnova 1 kiloton for being extremely sensitive to supernova neutrinos. We will see in a moment. So we said radioactivity, it's an issue, especially radioactivity of lead. And archaeological lead is particularly interesting because of the extremely low content of lead-210. This is a natural occurring radioactive isotope with a Q value of 60 keV. So this will fall exactly in our region of interest, which lies at the energy threshold, few keV, as we said. And this has an half-life of 22 years. So whenever this is embedded in our detector, we need to wait hundreds of years before getting rid of it. And luckily for us, the Roman made all the job for us. And we can exploit this material. So let's have a look at some numbers to have an idea. And in this table, we can see the concentration of radioactive impurities inside low background lead. In this case, I choose the Boliden lead, which is known for being extremely pure. And this has an extremely low concentration of thorium and uranium elements at the same level as archaeological lead. But when we look at lead-210, then here with the low background lead, we have 10 to the 7 microbecquerel per kilogram compared to some limits of 700 microbecquerel per kilogram in archaeological lead. And so this is the potential of this material, the extremely low concentration of lead-210. So the revolution of the word that we used at the very beginning of this talk, the revolution is here. We want to use archaeological lead not as a passive detector component, as it is done until now using archaeological lead, but we want to use it active detector component. So building detector with archaeological lead inside. And so, yes, so I added this slide just a few minutes before this presentation, because I always get the question of, so how about the kinematics? So lead is very nice because, as I said, the cross section is high. If you use archaeological lead, the background is very low, but lead is a heavy element. It's heavy, and so the signal that you are expecting to absorb is extremely low energy. So we need a very low energy threshold. And so here I try to address this point. So here on the left, we see a neutrino energy spectrum from a supernova. In this case, I choose a failed core collapse supernova, so a supernova that is producing a black hole. And I made a convolution of this signal with a detector response of a cryogenic detector. We define neutron number and proton number. And I've produced this heat map where each pixel represents an element of the periodic table, and the color represents the detector counting rate for an energy threshold of 1 keV. And well, if we draw ISO counting rate line on this plot, which is shown here, then we see, then okay, all the markers are different elements which are mostly used for building particle detectors. Then we see that with LED and only an energy threshold of 1 keV, we can achieve a detector counting, one of the highest detector counting rate among all these different elements which are currently used for building detectors. So yes, it's a very heavy target material, but it's already with the energy threshold of 1 keV, which is something not prohibitive, then we can achieve a very good counting rate, better than other experiments. And obviously, if we will be able to reduce the energy threshold, our detector counting rate would increase because we are expecting to observe an exponential, a signal which is exponentially increasing at lower energy. So how interesting would be to reduce the detector energy threshold? Well, I try to show this aspect in this plot, where you can see the detector counting rate as a function of the detector energy threshold for different elements. 1 keV is here, this dashed line, and we see that LED is as one of the highest counting rate. And if we're able to reduce the detector counting rate by 1 order of magnitude, so 0.1 keV, then obviously the counting rate will increase, but only about 50%. Let's say we will go from 30 counts per ton to 45, slightly above 45. So an increase of 50% for 1 order of magnitude lower energy threshold. So yes, it will be beneficial to have lower energy threshold, but I would say it's not mandatory, given that the improvement will not be that significant for such a big effort, 1 order of magnitude lower energy. And so, having addressed this point of the energy threshold, background, technology, the technical channel, if we're able to nail all these different aspects, then we can really build a powerful detector. And the potential of this technology is shown here, where we can see that the detector counting rate per unit of detector volume for different technologies for a possible next galactic supernova. We can see that with Resnova, we can achieve very large statistics with a moderate detector volume, 200 events per cubic meter with respect to 0 point something for water Cherenkov and Lepton scintillator. And with these very large statistics, we can perform detailed studies of supernovae, as we said, perform studies on core collapse physics, characterize the supernova remnants, the radius of the supernova of the neutron stars, or the properties of the black hole, but also perform studies on the neutrino mass properties, absolute mass scale or mass hierarchy, and also multi-messenger astronomy contribution. So Resnova, it's very nice, great potential, but it's fair to be said that the scalability of this technology is not as good and as easy as the one of water Cherenkov and Lepton scintillator. This is fair to be said. And this is shown actually here, where we see the number of detected events using neutral current processes as a function of the detector linear dimension. Different colors here represent different technologies. And we can see that with the water Cherenkov, we can build detectors with linear dimension of the order almost 10,000 centimeters. So something extremely big, tens, almost hundreds of meters of dimension. So something extremely huge. And obviously with the cryogenic technology, this is impossible to be imagined. This is really sci-fi. However, the Resnova technology has still a great potential. And here, let's have a look at the red curves. Here we see the number of detected events for 1 keV of energy threshold for one single unit, one single detector. Then Resnova demonstrator, the one that we were funded for, so the 30 centimeter side cube. Then Resnova phase 1, that has a total volume of equivalent to a cube of 60 centimeter side, so something that is really extremely compact. And if we are able to run a Resnova phase 2, with an energy threshold of 1 keV, and something that could fit ideally in a cryostat similar to the Core one, then we could get a sensitivity similar to the one of Juno and Hyper K, Super K. So even we can still keep the Resnova detector small and be extremely sensitive. Obviously, it's important to say that it's not that the experiment that detects most of the neutrino is the best experiment. It's also about the quality of the data that you collect. So how well you can reconstruct the neutrino energy and the main supernova parameters. But we will come to this point in a moment in 2 slides. So we have defined the technology. So let's have a look how a neutrino signal will look like in a lead tungsten crystal cryogenic detector as the Resnova one. So this is shown here, nuclear recovery energy spectra produced by a supernova placed at 2 different distances, 3 kiloparsec, like Cassiopeia A, the latest galactic supernova, and this was very close to us. And the dashed line is 50 kiloparsec as far as the Large Magellanic Cloud supernova 1987. And obviously we see here that commercial LED, it's the background induced by commercial LED is hiding this signature, but when we implement the Resnova technology, then we can suppress the background in the region of interest by 4 orders of magnitude. And thanks to the cryogenic technology, we can push down the detector energy threshold to the keV, sub-keV scale. And here, the red line, dashed line, represents the energy threshold of currently running supernova neutrino detectors. Something, let's say, comparable to, obviously, Borexino and EVD. Okay, obviously, Borexino is not running anymore, but this is to give you an idea that this type of process of coherent elastic neutrino nuclear scattering can be observed only if you achieve an extremely low energy threshold. And these numbers here are actually the results of experiments, data that we were able to acquire with prototype detectors. Those are not only on paper, so actually results and published results. But with Resnova, we can not only work and detect the neutrino energy, but also we can provide information about the timing of the arrival of the neutrinos. In fact, we are aiming at achieving a time resolution not prohibitive at all of 0.1 millisecond. And with this time resolution, we can identify all the different structure in the neutrino emission, provided that we have large statistics. So we can work on these 2 aspects, energy threshold and timing. And when we combine these 2 information, then we can really see how powerful is Resnova and this technology, and how we can contribute to the scientific community. And here we come back to the point that we said before about the quality of the data that you can acquire and collect. And we perform some likelihood studies where we try to understand which is the precision that we can achieve in reconstructing the main supernova parameters while running a lead tungstate crystal like Resnova. And the results of our studies are shown here. Obviously, those are only Monte Carlo simulation combined with likelihood studies. But with Resnova phase 1, so the 60 centimeter side cube, we can reconstruct the total energy of the star, which goes into neutrinos, with a precision of 30%, something which is comparable with the one of Super K with the gadolinium upgrade. And they can achieve a precision of about 25%. But in this case, we are mostly sensitive to muon and tau neutrinos. So we can provide complementary information to the currently running detector. And this is the best way in which we can really get a full understanding, a comprehensive collection of information from the next supernova. Given that these events have extremely low rate, it's important to be ready and extract all possible information whenever this will happen, because this will happen. Most people say this happened once in an academic career of a scientist. And given that 1987, I was only 4 years old, I still have some chances and hope that I will be able to observe it, possibly with Resnova. So coming to the last part of this talk, some experimental results. Obviously, everything that I've shown until now is based on some preliminary work that was done thanks to the support of INFN with some archaeological lab, some German institution, especially the Technical University of Munich, that provided some funding for running the detector demonstrator, and also, most importantly, I would say, also from Fedor's group and collaborators, they were able to provide us with a very first sample of lead tungsten crystal produced with archaeological lead. And so this was really key because we were able to show different aspects, especially three, which was extremely important for the beginning of this endeavor. The first thing that we were able to demonstrate is that lead tungsten crystal from archaeological lead can be produced and can be operated as cryogenic detectors. This is extremely important because not many people believe that this was something actually that was possible to be done, to run these detectors produced from this strange material as cryogenic detector. And we were able to show this. We were also able to show that this detector, this crystal, can be operated as low energy threshold particle detectors. And this was done thanks to the support and the help of the Max Planck, the CREST Max Planck group in Munich, where we were able to evaporate a TS, a CREST-like TS, on a small size lead tungsten crystal and run this as a particle detector. And we were able to achieve an energy threshold, really an excellent energy threshold of 300 electron volts for a detector which was a detector, say, thermal sensor and crystal, they were not at all optimized for this measurement. So just, say, off the shelf, we can get the 300 electron volt energy threshold. And this is the starting point for the development of the Resnova technology. Then we were also able to show that we can run detectors in an extremely low background environment with low background. And we perform a measurement in the Gran Sasso lab where we ran an almost a kilogram scale detector with in low background condition. We've investigated the radio purity, the concentration of the radioactive impurities in this crystal, and this has shown an excellent radio purity level. And the numbers that we were able to measure, the content radioactivity is shown here. As you can see, most of them are limits, some of them are values. And if we plug this number into our background model, then the projection of background that we get, it's this one, 9 × 10⁻³ counts per kV per ton per second, an extremely low background, and also extremely strange units, as many people point out. Strange units that, however, I think they exactly fit this, this framework. And this because supernova signal develop over time scale of some seconds, as we said, and so we need these units. Then obviously we need detector sizes at the level of hundreds of kilos of tons to detect this neutrino. Still some mass is needed, and so this is the reason for using ton and seconds. Then coming back to the radio purity of the crystals, the target goal for all the different elements is this one that is shown here. So in some cases we exceed our goal, which is extremely good. In some other cases we need to work on some details, but we know very well where to act in order to achieve our goal of 1 × 10⁻³ counts per kV per ton per second. Then, as I said, we developed a background model where we studied how the detector responds to different background sources, radioactive background sources placed in different detector components. Crystals, the copper structure, holding structure of the detector, bulk and surface contamination, and also Teflon, PTFE holders that are holding the crystal in place. And we have also considered external backgrounds induced by neutrons. And we have studied the detector response to these different background sources. And as a summary of the, let's say, of our studies, here we see the results. In this histogram plot, we see the detector counting rate in the region of interest, from 1 to 40 keV, so integrated, as a function of the detector multiplicity. Resnova will be a modular detector, and so we need to compute the background in the same way in which we will compute the signal. Signal will be many neutrinos will hit different crystal in a fixed time windows, because we, as we said, we are expecting a burst of neutrino. In the same way, we should compute the background. So many different crystal will be triggered in a fixed time window by different background sources. And what we observed is that as the detector multiplicity increases, the background decreases. And this is clear, obviously, because the probability of accidental coincidences decreases over the multiplicity. And we have considered as a coincidence window the 3 different phases of the emission. So neutronization phase that lasts about 0.1 second, the accretion phase that lasts about 1 second, and the cooling phase 10 seconds. And we have looked at the coincidence, this broad time window. And the bars here represent the expected background range. In the case in which we are not able to perform any particle discrimination, the top side, so we integrate all the events in the region of interest, and the lowest side is where we are able to perform a full particle discrimination, so rejecting all events which are not nuclear recoiled. And so finally, we will fall something in between this bar. And here on the right, we show the expected signal in the accretion phase from a supernova at 10 kiloparsec. The black line is the total integrated background from our simulation, and the dashed line is the neutrino signal. So a very clear signature. And so finally, numbers, the expected, our background goal is 10 to the minus 3 counts per ton per keV per second when the detector is operated in coincidence mode, which means 2 or more detectors trigger in the same time window. And which, if you want to convert these units in kilogram day units, counts keV kilogram day, well, the number is 0.086. So an extremely low background experiment. So finally, coming close to the end of this talk, sensitivity, we had a look at the background and the signal. This is the signal significance that we can achieve as a function of the distance of the supernova. And with the Resnova demonstrator, the light blue line here, we can almost cover the entire Milky Way by running this small size detector with only 1 keV of energy threshold. And then obviously by increasing the mass, we will increase the sensitivity. And we are only limited by the detector dimensions and not by the detector background. Then here I've also shown a red line, and this is the red line is the region where detectors might be affected by pileup. So if the supernova happens very nearby, then we will see a huge tons of neutrinos hitting our detectors. And this might be a problem because especially in the case of conventional monolithic detectors, then we will almost become blind due to pileup events. And so we made a study about how well we can reconstruct the information of neutrinos if a supernova explodes nearby us, very close to us, as it was the case, for example, of Cassiopeia A. And with Resnova, thanks to the modularity of the detector, we have negligible information loss from a supernova like Betelgeuse at 200, 300 parsec that can explode. While other detectors, like, for example, Xeno and Ton or Dark Side, due to the fact that those are very large volume, single volume TPCs, there are some time needed for the electrons to drift, and this slow down the time response to the detector, or like Super K with gadolinium, given that some time is needed for the capture of the neutrons, then the signal are somehow slowed down. But in our case, the modularity helps us a lot. And we have really negligible information loss with this technology, modular technology. Then, obviously, once you run a very nice detector with low background, if you are able to detect supernova neutrinos, you could detect, in principle, also solar neutrinos, provided that you have a low enough energy threshold. And in this case, Here on the left, we see the solar neutrino energy spectrum. The energy of the neutrinos is of the order of few MeV, 1 to MeV, while for supernova neutrinos, we are talking about 1 order of magnitude higher energy, 10, 20, 30, 40 MeV. So we will need an energy threshold, let's say 1 order of magnitude lower, something which is not easy at all to be achieved, but in principle, if we're able to achieve it, then the solar neutrino rate in a Resnova-like detector will double the one of boron xenon. So still, we could provide some information, complementary information to the one already very well established information provided by boron xenon, obviously. Then we could provide the contribution also in other sector not connected with directly with astrophysical neutrino sources, as it would be the case of dark matter. We said the signature that we're expecting from supernova neutrinos is similar to the one of dark matter particles, low energy nuclear recoil. And if we're running a low background experiment, then we could detect, we can establish very good limits on spin independent interaction of neutrino of dark matter with regular matter. And in this plot here, we probably is not the most updated plot. However, if we look at the lines, in green is Resnova, the dashed line is the sensitivity that we can achieve by running a couple of detectors, I think 5 Resnova detector for a month, and we can start to explore new region on the parameter space of dark matter spin interaction. Spin independent interaction, sorry. And the continuous line is when we are able to run the full detector continuously for 1 year. So we can cover the region in between 1 to 10 GeV and being complementary to experiments like xenon. So really, we can also provide important information on this. Nonetheless, we could also provide valuable results on double beta decay sector, in particular on the double electron capture of tungsten isotopes. Given that the detector that we are planning to run has a very large mass, the content of tungsten 180 will be rather large, of some few gram. And also in this sector, we could provide information. And also the scientific community has seen Resnova as a very interesting detector, and they have provided some physics cases in which Resnova could provide important information, both at the nuclear physics level and also at the astrophysical level, like the study of primordial black holes or diffuse supernova neutrino backgrounds. And so this is just a picture to highlight all the different physics that we can study with Resnova, and if we're able to run Resnova with the expected performance, obviously. So last slide, are we ready to detect the next supernova? Well, the answer, I would say, is no. Why? Well, neutrino from supernova 1987 took more than 100,000 years before reaching the Earth. So this means that neutrinos from the next supernova are already traveling to us, because the expected rate in our galaxy is 1 supernova every 50 years. So neutrinos are already traveling to us, but we are not ready to detect them, especially here in Europe, because most of the most advanced neutrino observatory went offline. See boron xenon and see LVD. And so this is really a unique opportunity for Resnova for being online at the right time. And luckily, well, I mean, we were lucky enough to be funded, let's say, by with a lot of funding by the European community. This allows us to plan for a long-term science program. We are able to provide results not only in the supernova neutrino sector, and this is extremely important because we need to run for many years, and we need to provide also other results, not only on supernova neutrinos. And we are in a very good status because we already proved the feasibility of our technology. And so we are almost ready. We only need to build up our detector, which is something that will be extremely difficult, but we are very excited and motivated for this. And so with this, I'm done, and I'm very happy to take any question, doubt, curiosity that you have.
Thank you very much for very interesting talk. And Okay, may I ask first question?
Absolutely.
Well, maybe two questions more. First of all, the principle itself is, I mean, this detection of neutrino via this way is checked in artificial neutrino sources like accelerator, for example.
So, okay. As I said, this coherent elastic neutrino nuclear scattering process was observed in 2017, and it's been observed, let's say, currently there are about almost three different nuclei in which this process was observed. Iodine, argon, and doesn't took my mind also the other one, and all the cross section that were measured, let's say, within the statistical error and the systematic error are within the standard model prediction. So in this case, the process is not showing any unexpected behavior. The only behavior might come from the fact that we don't know very well the nuclear form factor, because nuclear form factor ideally, I mean, usually are derived from this measurement. So using coherent elastic neutrino nuclear scattering, knowing the cross section and extracting the let me take the slides so that we talk about something visible. So usually they shoot neutrinos, knowing the energy, knowing the cross section, assuming from the standard model cross section, they derive nuclear form factor. In our case, the main advantage of lead is that the nuclear form factor of lead is the only element for which the nuclear form factor are independently measured using asymmetry parity violation measurements. This is some experiment where they shoot electrons on a lead target, and they look at the distribution, how they scatter, and from this they can derive the weak nuclear form factor. And so the main uncertainty in the cross section for lead is independently measured, and this is really something unique, because the only, say, uncertainty in this case would be, in this formula, would be, the only uncertainty will be on the neutrino energy, something that we, at the end, we want to measure. So, yes, the expectation are very, I mean, we are expecting to have a very, say, small error in the cross-section measurement. However, on lead, no, it was never measured yet. Could be possible to measure it at accelerator, yes.
And I think also tungsten is also sensitive nucleus for this. It also has cross section comparable with lead, of course lower, but is comparable, I think. Yes. So it also should be checked for form factor and so on.
Yes, let's say that we decided to choose lead tungstate for many different reasons. And one of the reasons is connected to tungsten also, because obviously at the very, very beginning, we said, okay, let's try to run pure lead crystals and run them as cryogenic detector. We tried our best with all the energies that we had, but unfortunately, yes, we are able to run as cryogenic detector, but with a very poor sensitivity, very poor energy threshold. So we needed to shift it to another compound. Another compound means having other elements in the molecule. And we wanted to have elements with a large neutron number. So we decided whether we go for lead molybdate or lead tungstate. And finally, we decided for lead tungstate because of tungsten, a higher neutron number, and also because we think that lead tungstate is somehow a more commercial crystal. So the technology, large scale production technology is already available, and I think this could be a really good selling point. The fact that we don't need to specifically design or produce something, but we can already use something which is available on the market, provided that radio purity of archaeological lead is preserved, obviously.
Mm-hmm. Thank you very much. Please, questions? More questions? Feder, would you?
So, Luca, I hope that purification of lead, if it is already enough pure in lead 210, can be organized. But what is your opinion about tungsten? Because in principle, tungsten oxide can, as compound necessary for crystal growth, can be a source of some contamination. And from my point of view, lead even easier to purify because we have experience to purify by distillation, by zone melting, and so on. What do you have already some ideas about purification of tungsten?
Yes, the answer is yes. And I was going to look for some numbers to give you, but anyway, at the moment we have identified as a producer for Resnova SICAS in China, and they have experience in producing lead tungsten crystals for high energy physics application, and they were interested in helping us in this endeavor. Obviously, they use Bridgman, and we did some tests with their materials, and they already did some production of test crystals. And we asked them to provide us some tungsten oxide to be measured and screened. They actually it's not SICAT itself they produce it, but they get support from an external company in Jialing. And we measured this lead tungsten. It was extremely pure. So I'm a member of the CREST collaboration, and I've been trying to, and I oversee the crystal production. And in the last year and a half, I tried to look for a producer which was able to produce lead tungsten crystal clean with the low uranium and thorium, and I was not able to find anything. I also tried some producer that you suggested me some time ago. I remember New Metal in Japan, and I also bought some samples for them, but nothing. High concentration at the level of hundreds of millibecquerel per kilogram. I measured this one from SICAS, and it was extremely pure. And I would like to give you the numbers here live. I just need to find the data. But okay.
It was some doubt about radium, you remember?
Yes.
But what about radium in this tungsten?
Okay. Okay, uranium and thorium ICP-MS measurement are, let's say, below uranium, below 12 millibecquerel per kilo, and thorium below 4. And radium, hold on a second. I don't know if I'm wasting too much time, but I should have prepared. But it was at... No, I don't want to say any stupid thing. I need to look at the number. HPG. Okay, here. Okay. Radium 228 from the thorium chain. It's below 1 millibecquerel per kilo. Mm-hmm. It's a limit. And radium 226, uranium chain, which is the dangerous element, radium 226. It's 0.9 millibecquerel per kilogram.
Oh, okay. And this is
just the raw material.
Tungsten oxide. And
yes.
This is because during the crystal growth, we hope it would be further purified. Okay,
exactly.
Very good.
Exactly.
Thank you.
And this material, from the radio purity point of view, it's very good. And also from the chemical point of view, because it's good enough for them for growing crystal. In fact, we were able to run crystals as cryogenic detector with good cryogenic performance produced from this tungsten. So, I mean, I'm super excited because tungsten is there, the lead is there, the crystal production technology, it's easy, I like to say. So, I mean, it's we have all the ingredients for making a very nice and tasty cake. We just need to cook it.
Heather, microphone.
Contamination of lead 210 is low enough in the lead in your possession, right? You have.
Yes. So we are at the moment we are discussing with INFN exactly which lead it's available. It could be used because there are different batches that are available. Some which was processed by quarry, and so some leftovers. Some that need to be completely processed. Some other that were already purified, and so we are at the moment discussing which one is available, and obviously we will the one that we select, we will make ICP-MS measurement and also some gamma measurement to make sure that the lead 210 it's low enough.
Okay, but I think that final measurements for to check level necessary for the experiment can be done only by bolometric measurement, right?
Yes, okay. Lead 210. Yes, it's
yes.
So either you detect the 803 keV from polonium, but
yes,
this has a very low branching ratio. So either you have a lot of activity, or it's difficult, or yes, or cryogenic measurement is the best. Either with a pure lead crystal sample, or also somehow a passive measurement in which a slab of lead is placed next to some cryogenic detector, something like this. So, okay. But yes, cryogenic measurement is the only one that allows us to achieve a very, very good sensitivity.
Okay, thank you.
Okay, more questions? You're welcome.
Well, if there are no questions and there are time,
I have one question. Sorry, I have one question. Usually people ask me, is there enough archaeological lead for the experiment and for the upgrade? And usually I always get this question from everyone. The answer is yes, 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 yes. So in Gran Sasso, there are some tons of archaeological lead available, tons, but from underwater, in Sardinia, they have extracted like I think 500 lead bricks. Each brick has a weight of variable about 30 kilos. So there is really enough material for running a Resnova 1 kiloton. Obviously, we don't want to do this, but there is enough for everyone, let's say.
Okay, but maybe not only this experiment need archaeological lead.
Yes,
of course,
it's as I said, it's a very valuable material. Absolutely, it's a very valuable material for shielding detectors, and especially why it's interesting for shielding materials. The main concern is the Bremsstrahlung of Bismuth 210. That gives a not negligible contribution in the low energy threshold detector. And also in the case of Resnova, we will need to work a little bit in defining the best geometry and design for our shielding.
Mm-hmm. Thank you. Vasil Debishuk, you're welcome.
Yes, thanks. Many thanks for the very captivating talk. I found it very informative for me. I'm from another sector. I'm working in high energy physics, but I think in somehow related related studies, because I'm working on the coherent production of J-psi meson in ultra-peripheral lead-lead collisions. So there are many similar physics in the processes you are studying, and in my case. So, but the question is, I think maybe is technical, but I think it is crucial. What is the importance of the time resolution in your studies, because in my case we need to discriminate the processes with the precision of somehow 25 nanoseconds, so on. So you said that in your case the time resolution is about 1/10 of millisecond. Is it crucial to obtain the better time resolution to discriminate the pure signals of coherent scattering of neutrinos? Thanks.
Okay, thank you very much for your question. It's very interesting to see how people from a different say sector see these things. So yes, time resolution. These detectors are say extremely slow, as I said, cryogenic detectors, and the time resolution of our detector will depend on two main parameters, and the first one is the crystal dimension. And the second one is the temperature sensor design. Order of magnitude, a pulse, a thermal pulse in our crystal is expected to have a length of some 100 milliseconds, let's say, the pulse. And we want to be able to measure precisely the onset of the pulse. And so this is defined more or less the resolution that we say the precision, the resolution that we can get on the rise time of the pulse. And so being slower than 0.1 millisecond, then say we get 1 millisecond, then you can see it here. I mean, it's this picture, this plot will be smeared, and structure on the lower side of the plot will be smeared and hidden, while still we could reconstruct all these strange features in the accretion phase. So let's say that the main goal would be ideally to reconstruct the structure at the 200, 300 millisecond time scale. So once we are able to identify the precise time of each single neutrino interaction in the different crystal, then we can build this entire picture like this. But yeah, I mean, it's an additional information that we could get, and obviously, if you have a good time resolution, you can define precisely when is the onset of the first neutrino. And this information is crucial that you can share it with other supernova neutrino detector around the world, such that if they have higher background, they can precisely tag set the trigger, and being more sensitive for this. And there is an interesting study in literature. Maybe I have it here. I don't know. And that is shown that neutrino, you can use the neutrino, the arrival time of neutrinos as trigger for gravitational waves detector. And if you are able to provide them the exact timing of the neutrino signal, they are able to increase their sensitivity by almost a factor of 5 in their search, because they can obviously they do some match filtering, and they can precisely select the window, the size of the window in which they need to look for the gravitational wave signal. In the other case, in which they don't have a trigger, they have to look for a broad window, and obviously their sensitivity is smeared and is reduced.
Okay, thanks.
Thank you. More questions? Mykola, you're welcome.
Thank you for a very interesting presentation. I have a question about the background level and how is this crucial to this kind of experiment, because I'm drawing parallel to double beta decays. It's more familiar research field for me. But I wonder how useful is the experience of building low background experimental setups like Huor and Cupid, all this in future that used for double beta decays. But as you mentioned, that setup is built in like similar way with the crystals and everything. And I just wonder how useful is that experience from double beta decay experiments, because range of interest is like different, because for double beta decay it's high energies, but here is again low energies like 10 keV and around. And are there any issues with it, any specific issues? So that's my question.
Thank you very much. So yes, background is extremely important, absolutely, because I mean, we want to archaeological lead. It's a very nice material, as we said. Also, the tungsten is extremely good, and we want to take full advantage of this material, of the radio purity. The background that we want to achieve is 10 to the is 10 to the minus 3 with these strange units. So ideally, if we could be, if the background, we will not be able to achieve our background goal, what will happen? Let me take the plot. What will happen is that we will be able to explore a smaller region of our galaxy. So still we will be sensitive, but we will not be able to go as far as we are expecting. So background is important because of this. Why this background level? Well, if you take all the numbers, the knowledge that we have about background inside copper components, inside archaeological lead and tungsten, then if you do the simulation, then a conservative number that you can get is this 10 to the minus 3. This means that the expected, so naively speaking, the number of background events that you are expecting in a time window of about 10 seconds, it's less than 1. So ideally, we could live enough well if the background is slightly higher. However, I mean, we want to develop a technology. This is a technology demonstrator. So we want to show that we can achieve extremely low background level. And if we are able to show this, then in principle, I mean, being more sensitive, it's only a matter of increasing the mass, adding more crystals, and not do any work on the background. So background is extremely important because allows us to go farther in space and might help us in the next upgrade of the experiment. And in addition, if the background that we are able to achieve is extremely low, then we can do other studies in other physics sectors, as for example, dark matter experiment in this case. But overall, comparing to double beta decay, this level of background are, let's say, worse than the one which are needed for double beta decay experiments. Are higher because a low threshold is more difficult to reduce the background, and but also because in some cases it's not fully needed, because supernova neutrino signal, they have this specific structure. So ideally, if you see a sort of a modulation of your signal, your background with that shape in your region of interest, then you can easily identify the arrival of neutrinos. But in the case of double beta decay and dark matter, you don't know when the signal is coming, and this signal have no time structure. So in this case, for supernova neutrino, it's a little bit easier, and some constraint on the background can be released. But if you want to do other physics studies as dark matter, then you need to work hard on the background.
I understand. Thank you very much.
Thank you. More questions? Okay, we are just in time, practically, as we expected. So again, say that we are very grateful to Professor Pattavina for his very interesting lecture. So,
thank you.
And actually, I found very many interesting things in it. I have some experience with bolometers, but just this one sector is very interesting, very new for me, of course. And thank you again, and thank you for all people who present on this lecture.
Also, and from my side, thank you very much for attending.
And thank you also for answer for our questions.
And yeah, I'm very happy. Thank you very much. It was very nice. And yeah, I hope to see some of you live, let's say in Gran Sasso, hopefully. And yeah, thank you very much again for your kind invitation.
And
Okay.
let's hope that neutrino will not neutrino burst will not reach Earth before detector will be proven.
Absolutely. There is one supernova explosion for academic career. So
Yeah.
Okay,
Thank you very
actually,
much.
yes. Okay, I know, by the way, that astronomers lost one explosions of galactic supernova in last century. It was found only only post factum.
okay.
But we don't have the we did not have neutrino detectors at the beginning of 20th century, so we didn't find it. Okay, thank you again, and
Thank you very
our
much,
lecture
all.
is finished. Bye. Goodbye.
Bye bye. Bye bye. Bye bye.
Goodbye.
Everyone.
Thank you. Bye.